Hello friends, here in this video we will see a problem on design of helical compression spring, and for that here we have a question. I'll read what is given here. Design a helical compression spring to carry a load of 500 Newton with a deflection of 25 mm. The spring index may be taken as 8. Assume following values for spring material. Tau, that is shear stress, is equal to 350 Newton per mm square. Capital G, that is modulus of rigidity, 84 kilonewton per mm square. Now for these data which is given, we have to design a helical compression spring. From the data, here I'll write whatever is given. Here we have to design a helical compression spring to carry a load of 500 Newton. So W is equal to 500 Newton with a deflection of 25 mm. Deflection, that is 25 mm, denoted by delta. The spring index may be taken as 8, so capital C is equal to 8. Assume the following values for spring material. Tau and G values are given. Tau is 350 Newton per mm square, and G, which is modulus of rigidity, 84 kilonewton per mm square. I'll convert this, so this becomes 84 into 10 raised to 3 Newton per mm square. Now for these data available, let us try to design the spring. So in the solution for this problem, since the value of load and deflection they are given, the first thing which I can calculate here is the stiffness of the spring. So here I'll write down stiffness of the spring is given by, stiffness is denoted by capital K, and that is equal to load upon deflection. Here I'll put the values. K is equal to load, it is 500, deflection is 25, so here I get the stiffness as 20 Newton per mm. So the spring will deflect by 1 mm when the load on the spring is 20 Newton. Now after getting the stiffness, I'll write down, since spring index is given by, spring index is capital C, and that is equal to capital D upon small d, where capital D, it is called as mean coil diameter and small d is called as wire diameter. This is the formula. Now from this I can say that therefore the value of capital D or small d, if I am able to get any one of them, I can get the other value, because C, spring index, is given in the problem as 8. So if you know any one of the values, you can calculate the other values. So here I write down, therefore capital D will be C into small d. I'll keep this as my equation number 1. Once I know the value of small d, I'll put it in equation 1 to get the answer of capital D. Next, now in this problem, as shear stress is given, tau is equal to 350 Newton per mm square. So here I'll calculate the shear stress factor, since shear stress factor is given by K suffix S is equal to 1 plus 1 upon 2C. This is the formula of shear stress factor, and in this problem, as the value of C is given, I can find out K suffix S, that is 1 plus 1 upon 2 into C, that is 8. So if I calculate from this the answer of shear stress factor, it comes out to be 1.0625. Now after getting the shear stress factor, I can use the formula of resultant shear stress, because this tau value which they have given in the problem, it is the resultant shear stress. So I'll write down, since resultant shear stress is given by, the formula is tau is equal to 8WD upon pi d cube multiplied by Ks. This is the formula of resultant shear stress. Now here, as I can see in this formula, there is one relation of capital D upon small d. Means capital D upon small d, that is mean coil diameter upon the diameter of wire, that is equal to C, which is spring index. So here in this formula I can simplify it in one more way, that shear stress will be equal to 8W, capital D upon small d is C, so in the denominator there is pi and d square will be left into Ks. I'll write down into the bracket, since C is equal to capital D upon small d. Now if I look into this equation, shear stress is given in the problem as 350, load is there, spring index and shear stress factor we have calculated just now. So only unknown which is left is d square, which is the mean coil, which is the diameter of wire, small d. So here I'll write it down as, therefore shifting d square on one side, I'll shift this term because I want to calculate d. So d square will be equal to 8WC upon pi into tau multiplied by Ks. Here I have shifted d square on left hand side, tau will be here in the denominator on right hand side. So now I'll just go on putting the values, that is d square will be equal to 8 into W is 500, C is 8 upon pi into tau, it is 350, multiplied by Ks, shear stress factor was 1.0625. Therefore, now from this, if I calculate here, I'll get an answer, and if I take the square root of that answer, I'll get the value for D, and small d value, it comes out to be 5.56. I can round off this value, I'll say that, or this is 6 mm. So now here, after getting the value of small d, this will be our answer number 1. That is, here we have designed how much should be the wire diameter, and its cross section will be circular, and here this is the wire diameter denoted by small d, its value is 6 mm. Now after getting the value of small d, here I'll put this value in equation number 1 and I'll get the value of capital D. Therefore, put small d is equal to 6 mm in equation number 1. So therefore we have capital D is equal to C into D. C is 8 and small d is 6. So here I get the value of capital D as 48 mm. This is our second answer. So here I have got the mean coil diameter. Next, after this, I'll use the formula of deflection to get the number of turns which are there in a spring. I'll write down, since deflection is given by 8W d cube n upon GD raised to 4. This is the formula of deflection. Now again, in this formula, what we can do is that either we can put the values of capital D or small d, or we can write the formula in the form of small c, which is the spring index. So even if I simplify this, I'll get it as deflection is equal to 8W. Capital D upon small d is spring index. So spring index C cube into N upon, here I am left with only G into D into bracket, since capital C is equal to capital D by small d. So therefore here I want to calculate N, that is the number of active coils. So N will be equal to deflection, this GD term will go onto the left hand side, and in the denominator it will be 8WC cube. So putting the values here, deflection, it was given in the problem as 25, G it was 84 into 10 raised to 3, small d value we have calculated, it is 6 upon 8 into W 500, C it was 8 cube. So from this, if I calculate, I'll get the number of turns as 6.15, which I can round it off to 8. Means 8 number of active coils are required. So I'll say that therefore number of active coils is equal to 8. So here, after getting the values of wire diameter and mean coil diameter, the next value is number of active coils. This is our third answer. Now, number of active coils means those coils which take part in the deflection. Apart from this, there would be one coil at the top and another at the bottom which do not take part in the deflection. So here I'll find out total number of coils. Therefore, I'll write down, assuming squared and ground ends, total number of coils will be equal to number of active coils, which is N, plus 2. When we are using squared and ground ends, then the total number of coils would be N plus 2. So therefore, total number of coils, I'll denote it by N dash, is equal to N, it is 8 plus 2. So the total number of coils required are 10. Next, here I'll write down, after getting the total number of coils, this will be the fourth answer for us. Next, after getting the total number of coils, now I can say that since solid length of spring, solid length is denoted by L suffix S, and that is n dash multiplied by the diameter of wire. So here we have n dash as 10, diameter of wire is 6, so therefore solid length becomes 60 millimeters. Solid length, I can explain it with the help of a diagram. Here I am drawing the diagram for solid length. Now, this solid length indicates this is the length of the spring in completely closed condition. That is, when we are applying the load, this spring would be compressed under the action of load, since we are using or we are designing the helical compression spring. So when the load is applied, and then there should not be any gap between the turns of the spring or coils of the spring. So when it is completely closed, each of the wire diameters, they are in contact, then this complete length would be called as the solid length of the spring. So while designing, we should even know how much should be the solid length. Next, I'll calculate free length of spring. Free length of spring, that is LF is equal to solid length plus maximum deflection plus 15%. If I write it in the form of number, it is 0.15 of maximum deflection. So this is the formula to calculate the free length of the spring. I'll go on putting the values. LF is equal to solid length is 60, maximum deflection is given in the question, it is 25 mm. Yes, it is 25, plus 15% of maximum deflection, which is 25, and so my answer of free length, it comes out to be 88.75 mm. This will be our sixth answer. After getting the free length of the spring, next I can calculate the pitch of spring. So after this, I'll say that, therefore, now before going on to pitch of the spring, here I'll explain what is free length. I'll explain what is the meaning of free length before going on to the pitch of the spring. Here I am drawing the diagram for the free length of spring, explaining what it is. Suppose we have a spring. Now the length of spring in the unloaded condition, that is when it is not loaded, then that indicates the free length of the spring. So here this complete length is the free length of the spring, and maximum deflection, it would be, we can measure it from the total, thus we are getting the deflection at each of the ends, so that would be the maximum deflection, and here is the pitch. So free length indicates the length of the spring in the unloaded condition. Now, after getting the free length of the spring, the next thing which we have to calculate, it is the pitch. So it is called as since pitch of coil, which is P is equal to, the formula is free length upon total number of coils, which is n dash minus 1. From this formula we can calculate how much is the pitch. So therefore pitch will be equal to, free length is 88.75 upon n dash minus 1. N dash was the total number of coils and the value was 10. So 10 minus 1. So here pitch comes out to be 9.86 mm. This is the 7th answer for us. Now after we have reached up till pitch, next I'll say that whatever dimensions we have found out, I will denote it on a diagram. Here I am again drawing a helical compression spring. This is the diagram for the helical compression spring. Here I have drawn the diagram. Now this indicates a helical compression spring. When we are applying load over this, load is given in the problem, it is 500 Newton. So under the action of 500 Newton load, this spring will compress, and here the first thing which we have found out was the wire diameter. Wire diameter is the small diameter here with the help of which the spring is made. It is this diameter. These are the wire diameters. So here in this problem we have got the wire diameter as small d is equal to 6 mm. Then the mean coil diameter, that is the line which is passing through the center of this wire on both the sides. This was the mean coil diameter and it was 48 mm. Next, after this we have calculated the solid length. Solid length was 60 mm. Free length of the spring, that was 88.75 mm. Then after getting solid length and free length, we had calculated the number of active coils, which was n, equal to 8. Active coils are these coils which are subjected to compression or which take part in the deflection. Apart from that, we have 1 and 2. These two turns of coil which do not take part in the compression because they are fixed. So total number of coils n dash, it was 10, because we were assuming that these coils, they were ground, they were squared and ground. Grinding was performed so that they can be seated here. So n dash is equal to 10. So in total here we have calculated one parameter, which is the wire diameter, second parameter which was the mean coil diameter, third parameter it was the number of turns, fourth total number of turns, then we have calculated solid length, and at last free length, and finally even pitch. Now what was pitch? If we take any point, any arbitrary point, like if I take this center, then on the next wire I have to take the center, that is the same point, and if I measure the distance between these 2 points, it would be called as one pitch, and the pitch value is 9.86 mm. So here we have completely designed this helical compression spring, helical compression spring, with all the dimensions on it. and in this video we have seen how to design a helical compression spring subjected to load, and there was some parameters given. With the help of that we have completely designed the spring.